We are now in Module 2, Part 2. In this section, we study the concept of BFSK generation and detection, that is, binary frequency shift keying, generation and detection, and non coherent detection of BFSK. And we are going to study DPSK concept. BFSK generation and detection, that is binary frequency shift keying, generation and detection. So in binary frequency shift keying, binary symbols ones and zeros are represented by equation as shown. Si of t is given by square root of 2eb by tb cos 2 pi fit. So here two signal we are transmitting to represent binary 1 and to represent binary 0. Therefore, I takes the value 1 and 2 here. Based on the two signal we transmit, the first signal in order to represent symbol 1 is represented by S1 of t is given by this equation. Similarly, for symbol 0, S2 of t, second type of signal with different frequency, that is given by this equation. So observe equation 2 and 3. The frequency of first wave and second wave are not same. Hence, we are going to maintain phase continuity in frequency shift keying, but the frequency different. Based on this equation, we can write orthonormal basis function. So here, observing equation 2 and 3, we are able to see here cosine term is common. Therefore, writing this square root of 2 by tb cos 2 pi fi of t as our orthonormal basis function, we can now able to obtain the vector coefficients based on the signal we transmitted Si of t and the orthonormal basis function, that is phi j of t. So what is the expression for vector coefficient? That is given by this expression integral 0 to tb Si of t phi j of t into dt. So what is Si of t? You substitute here. What is phi j of t? You substitute here from equation 4. Now we are able to get the expression for S1 of t in terms of the orthonormal basis function and vector value like this. Use orthonormal property in order to obtain this equation, that is integral 0 to tb phi I of t into phi j of t is equal to 1 if I is equal to j, otherwise it is 0. So now S2 of t is given by this expression phi 2 of t EB. So how to find a coefficient here Sij? So we are now trying to find the coefficient with respect to the signal we are going to transmit. What is S11? That is the first vector value of the first signal that is transmitted is given by S1 of t and phi 1 of t here. So what is that? S1 of t we write here and phi 1 of t also will write here. What is S1 of t? S1 of t is nothing but here square root of EB into phi 1 of t. You substitute here and apply orthonormal basis function property. You will get square root of EB here. Similarly, S12, that is the signal which is depending on the second orthonormal basis function. 1 stands for the signal S1 of t transmitted and 2 stands for second orthonormal basis function. So substitute S1 of t as shown here, EB into phi 1 of t here. By using orthonormal property here, integral 0 to t be phi 1 of t, phi 2 of t, because I is not equal to j, the second vector value here is 0. This is how we obtain the vector value for the first equation. Similarly, you try to find S21 and S22. Since I is not equal to j, this becomes 0, and since I is equal to j, I obtain here square root of EB. So write the values of S2 here. Once the coefficients of S1 and S2 vectors are known, we can draw the signal space diagram for FSK. What is the message point vector for S1? That is square root of EB and 0. And what is the message points for S2, signal S2? It is 0 and EB. So if this represent X and this represent Y coordinates, so let us write the orthonormal basis function as shown here on X axis and Y axis. So this is the origin. So the first message point X, that is S1, is given by here EB and 0. So on X axis move towards EB, and Y axis it is 0. Similarly for message point S2, that is M2. So here EB 0 and EB here move towards Y axis. So in order to obtain the region, so you connect these 2 points and draw one vertical line here, perpendicular line. So you are going to see two regions here, which is nothing but region Z1 to identify message 1 and message 2 here. In this slide, we are going to study binary FSK generation and binary FSK detection. So our main intention is to transmit binary information using analog signal on the analog channel. So we have observed here in our previous slide, the vector values are ranging from 0 to AB here. Therefore, the orthonormal basis functions also we know. So if this is the equation for two signal, that is S1 of t in order to represent binary 1 and S2 of t in order to represent binary 0, I have to obtain suitable encoding value in order to represent this binary value. So the first section here in the transmitter is encoder, on off level encoder, because we have here 0 and square root of EB. Square root of EB represent on and 0 represent off here. So now at this point, output of encoder, I am going to get EB or 0, depending on the input we are going to apply here. The next section is to generate binary FSK wave at any duration instant of time. Only one wave is to be generated, which is of frequency F1 or F2. Therefore, whenever this section is on, this section will be in off condition. Whenever this is in off condition, and this section will be in on condition. Hence, we are now going to analyze the working of this block diagram. So whenever the bit 1 you are transmitting, encoder will generate EB. Therefore, the upper branch is active and it will generate BFSK wave, that is, which is of one frequency. If the output of encoder is 0, because of inverter is here, this is inactive, the top branch is inactive and the bottom branch is active, and we are going to get the second wave of second frequency here. That is how BFSK waveform is generated. For example, binary 1, followed by binary 0. So here you can observe the difference in the frequency that is transmitted for every TB duration. Coherent detection of BFSK technique. Here the incoming signal x of t, which is nothing but the corrected signal, which is passed through the correlation receiver here, which is producing two vector values x1 and x2 as shown. So it is applied to the decision device, that is x1 minus x2. What is y? Y is x1 minus x2. So now this y is applied to decision device with threshold 0. So if the value of y is greater than 0, this decision device will generate binary value of 1 amplitude, suitable amplitude for TB duration. Otherwise, it will not generate anything. So the decision device output will be 0 for TB duration. That is how binary 1s and 0, whatever you transmit here, will be detected and regenerated at the receiver section. Since the carrier that is transmitted at the transmitter section is known at the receiver, therefore this technique is called coherent detection. So the next very important concept here is binary frequency shift keying using non-coherent detection. Here, the receiver consists of a pair of matched filter which is tuned to the two frequencies. This is F1 and this is F2. Now we are using the envelope detector after the matched filters. So here at every instance, this envelope detector sample is taken and we are going to obtain the values L1 and L2 here for every TB seconds. So there is a comparative device. So it compares the two value L1 and L2. If L1 is greater than L2, so this comparative device or comparison device will generate 1. Otherwise, it generates 0. So the next very important concept here is DPSK, differential phase shift keying. This is another technique in order to transmit the digital information. So in DPSK, we follow this algorithm. Whatever the bit we are transmitting, it is encoded. Therefore, if we consider the kth bit we want to transmit, so the differentially encoded kth bit transmitted is given by XNOR logic by using equation 24. It is nothing but bk dk minus 1 plus bk bar dk minus 1. What is dk minus 1? Dk minus 1 is nothing but the previous bit which is assumed to be 0 or 1. Since we use analog techniques to transmit the digital information over analog, if the dk bit is 1, binary 1, the phase transmitted is 0. If the kth bit is 0, that is encoded kth bit is 0, then the transmitted phase is 180 degree. So at the receiver, we are going to generate the polarity if the signal is passed through the integrator. If the present bit is equal to previous bit, then the integrator generates positive polarity. Otherwise, it will generate negative polarity. Based on this polarity, the decision device will detect whether 1 transmitted or 0 transmitted. So now we are going to analyze the transmitted bit and received bit for the sequence that is shown here. So this is the binary sequence that is shown 10010011. So you write the binary bits transmitted in the first row 1 0 0 1 0 0 1 1. Assume dk minus 1 bit is 1. You can assume it 0 also. So now in order to encode the bit to be transmitted, so you use the logic dk minus 1 bk plus dk minus 1 bar into bk bar. Use this logic, XNOR logic. According to XNOR logic, if both bits are same, then output is same as the bit. If both bits are different, output is 0. Here both are same, output is 1. Here both are same, output is 1. Here both the bits are previous and present bit are different, output is 0. Both are same, therefore output is 1. Hence, we are able to encode the transmitted bit like this. So what is the phase angle? So since we consider the previous bit is 0, phase is to be transmitted here is 0. And we are going to write the phases like this. 1 is transmitting, therefore it is 0. 0 is transmitting, phase is pi. Wherever 1 you are going to find, write 0 phase. Wherever 0, write 5 phase. Now what will be the polarity of the integrator? So you observe here the polarity of integrator here. The previous phase and the next bit phase is same, therefore positive polarity. dk minus 1 is equal to dk. Here dk minus 1 is not equal to dk, therefore polarity is negative. Similarly, polarity is negative. Polarity is positive because both bits are same. Polarity is negative here. Again, polarity is negative here. Since the polarity of intake phases of the previous bit and the present bit is same, therefore polarity we are going to get positive. So the decision device based on the polarity of this integrator will produce binary 1 or 0. For positive, it will produce 1. For negative, it produce 0. So this is the detail about DPSK. So now we'll try to understand the DPSK generation and DPSK reception. So generally, the first part of DPSK consists of a logic network. Here is your binary input. Some logic network should be there in order to provide XNOR function. So this is your output dk. The dk is nothing but bk dk minus 1 plus dk minus 1 bar into bk bar. So this output dk is applied to delay network in order to produce dk minus 1. So now this output encoded sequence is applied to BPSK modulator. That is nothing but here I have to produce the two amplitude in order to represent 0 and 1. Therefore, I am going to generate the amplitude that is 1 or minus 1 depending on the binary 1 or 0 transmitted here, and it is multiplied with here the product modulator with higher carrier frequency in order to represent DPSK signal. Since this is DPSK scheme is used, here amplitude level shifter will produce square root of EB or square root of minus EB, positive or negative amplitude here, which is multiplied with the cos signal. In a similar way, the reception block diagram for DPSK is as shown. The received signal is applied to the correlator here, and the correlator output is applied to product modulator with delay, which will generate the two values x0 and x1, which is added. Therefore, y is given by x0 plus x1. Now, this value is compared with the threshold. When the value y is greater than 0, binary 1 is generated, otherwise binary 0 will be detected. This is how the DPSK receiver will work. Possible important questions based on the topics that is given in the syllabus are like this. I have put here some of the extraction of previous year question paper. So here you are able to see generation and detection of BFSK. Since here nothing is mentioned coherent or non-coherent, it is left to you. So we can consider it as coherent detection and generation. You have to write signal space diagram for BPSK and derive probability of error. So given some binary sequence, you have to write QPSK signal. So you have to sketch again QPSK signal for this binary sequence shown. And for BPSK, you have to obtain probability of symbol error. And short notes on constellation diagram for QAM and to write its signal space diagram. And here in the next question, you are able to find BFSK and DPSK, encoding, decoding, everything you have to write here. The binary sequence is given, you have to obtain transmitter output and receiver output here, and a small problem on FSK system, followed by generation and detection of QPSK, DPSK, and the FSK non-coherent detection. All the topics in module 2 are very important and you can attend these questions. So that is the end of module 2 part 2.